forces parallel to the incline are equal. You can see what are the forces. You have got W2 and W1. You know, as you've been saying, when you're working on an incline, if you have got forces that are going downwards, they are going to have two components. You have got a component that goes in this direction and then a component that goes in this direction. The component that goes downwards, we call that as Fg. We'll call this Fg1. That will be the same with this one. To have these two components, we'll call this as Fg2. But we've been told that the components of the two forces parallel to the incline are equal, meaning that Fg1 is the same as Fg2. How do you find Fg? And this is just given by mg, the sine of the angle, isn't it? Okay, so that's what you put there, mg sine theta. And then this is going to be equal to the other side. And please take note of the masses. You have got different masses here. Okay, where there is again Fg, we are going to put mg sine, but the angle here is this angle like that. So that's number one. That's how we are going to put it there. And then the next thing now, we are going to make some substitutions at this point. What do we know here? We were told that W1 is the weight force is actually 2N. And then W2 was 5N. So this is weight. Mg is the weight. So where there is this mg, that's what we're going to substitute 2N. And then sine. Now remember the angle theta is 65. And that will be equal to this other mg, which is W2. Let me just put a W so that will not be confused. We'll put 5N. But sine, we don't know the angle. I'll remain with sine of this angle. So what do? We are going to divide both sides by 5N. So sine of this angle is going to be 2N sine 65 divided by 5N. This N will cancel with this N. So sine of that angle is going to be 2 sine 65 divided by 5. And that will be a 0.3625. If we want to remain with this angle, we'll take the sine inverse of 0.3625. So this question was just on forces. It's really not work, power, and energy. So this is going to be 21.26 degrees. I hope that's okay. Okay. Next question. A sky jumper slides from from rest down a 37-degree slope for 20 meters before taking off from a negligible short horizontal takeoff. The speed at takeoff is 15 meters per second. Find the coefficient of kinetic friction on the slide. Use the principle of conservation of energy. So if you can't interpret these questions, it will be very hard for you to answer. So first thing first, be able to interpret what are they asking. And in physics, the way we interpret questions is by using a diagram. Okay, so something like this. We've been told the sky jumper slides from rest down a 37 degree. So this guy was on a 37-degree incline. Taking off from a negligible short horizontal, so meaning that he was somewhere here, just like a short distance. Okay, and then he had to slide down. If the speed at takeoff is 15 meters, find the coefficient of kinetic friction. But remember, a sky jumper slides from rest, meaning at the maximum point here, the initial velocity is a zero. And then by the time this guy is reaching this point, he is now having a velocity of 15 meters per second. And then he will slide down like that. What is the height of the place from which he came? We don't know that yet, isn't it? Since we are using the principle of conservation of energy, and what have we been told? Coefficient of kinetic friction, find the coefficient of friction. For you to find the coefficient of friction, it means that there is actually friction on the incline. So in that case, when you are using the energies, you need to understand what is the energy on top. Because all the energy at the beginning should be equal to the energy at the end. That's the conservation of energy. So we say energy, let me just use simple initial. So energy initial is equal to energy final. So at the beginning, what energy do we have? At the top, what we have is potential energy. Okay. Or we can say energy at the top and energy at the bottom. That's the same. But besides that, because there is friction on this incline, friction is also going to be initial energy. Now, friction is going to be doing work, and that work is going to be subtracting. Or we can do this. Since at the beginning I only have potential energy, that potential energy is going to be converted to kinetic energy by the time we are reaching the bottom, plus also the energy that is going to be lost. Okay, the energy that is going to be lost. Now, where is this energy going to be lost? It's going to be lost because we are going to be doing work against friction. Take note of this. There's work done by friction and work done against friction. So at the maximum point, the kinetic energy is, the potential energy, that's mgh. At the bottom, the kinetic energy is half mv squared. The energy loss is the energy done by or done against friction. That is going to be, remember, this is energy. Since we have friction here, so it will be either done by friction or against friction. Is basically the same. If it is done by the friction, we are just considering in terms of the friction. Against friction, we're considering the other force. Energy by friction. And this is actually equal to work by friction. And how would you find that? It is simply friction force times the distance. So that will be mgh is equal to half mv squared plus kinetic friction is given by the coefficient of kinetic friction times the normal force. This is an incline. The normal force is mg cos theta. Okay. And then we'll multiply that by distance. So what am I saying? All I'm saying is that kinetic friction is equal to coefficient of kinetic friction times normal force. And then normal force itself is mg cos theta. So you just multiply this now by d. Can you see that mass is common? That's why for this question we are not even given the mass. So g is 9.8. The height of the fall, do we know the height here? We are told there is a slope and then the distance of 20 meters. But you know that height is d sine theta. So that is going to be 20 sine the angle is 37. And that is going to be equal to half. The final velocity is a 15 at the bottom, square that, plus mu k, gravity is 9.8. Can I start with d and then write cos theta? So that is 20. And then cos the angle theta is a 37. So start from the beginning, 9.8 times 20 times sin 37. That gives us 117.9557. And that will be equal to 15 squared times 1 over 2. That's 112.5. And then plus 9.8 by 20 by cos 37. That is 156.53. And then by mu k. For us to remain with mu k, we'll take the 112.5 the other side. So we're going to have 117.9557 minus 112.5. The answer we get, we divide by 156.53. And that will give us 0.03485. So that is it. Are we okay there? If you're okay, simply react if you don't want to speak. Okay. The next one is saying a 58 kg car is sliding a 25-degree slope as shown below near the top. So near the top, her speed is 3.6. So at this point, the speed is 3.6 meters per second. She accelerates down the slope because of the gravitational force, even though a kinetic friction force of magnitude 71 Newton opposes her motion. So there's actually friction of 71 Newtons opposing motion. Ignore air resistance. Determine her speed after sliding a distance of 57 meters. So the guy has to slide. The distance here is 57 meters. So what will be the speed at that point? We can use two methods. Let me use both so that we see what we are going to get. The first one we are going to use is the work energy theorem. From the work energy theory, you know that work is equal to change in kinetic energy. Kinetic change in kinetic energy is given by financial, not financial, but final. final kinetic energy minus initial kinetic energy. Because at this point you have got velocity, also at the beginning you have got velocity, so you actually have a difference in these velocities. And then how do you find the work now? So at the beginning, the work we have, remember the person is at the top, isn't it? What is causing this person to go downwards? Because we could have said work there is mgh, mass times gravity times the height. Of course, it's not hard to find the height because we could have just done this. But if we'll be doing that, that work we are using, that's potential energy. That one is when we are using the other method for conservation of energy. But here work, this person is being put downwards. So when it comes to the work, we have got a work due to gravity, okay, because the gravity is putting this person downwards. We also have work because of friction, and this will be equal to the change in kinetic energy, which is kinetic energy final minus kinetic energy initial. The work done by gravity, remember work is force times distance, but Fg itself, so I can say Fg times the distance plus work done by the friction is friction itself. Now friction by definition is negative. If you put friction in this formula, because it is together with work, it becomes negative. It's different if you put it to the other side of the equation and then times distance. That will be equal to kinetic energy, which is half m, so be final squared minus half m initial squared. Fg is given by mg sin theta, and then we multiply by d, and then we have got minus fd, that will be equal to half mv squared, this is final, minus half mi squared. The mass is 58, g is 9.8 sine 25, the distance covered is 57, the force of friction is 71, the distance is a 57, that will be equal to half, the mass again is a 58, we don't know the final velocity, minus half, the mass is 58, the initial velocity there is 3.6. So start at the beginning, 58 times 9.8 times, I'll multiply first by 57, and then I'll now multiply by sine 25. I'll get that answer and remove. So I'll subtract negative 71 times 57. So that gives us there 9645.324539. You punch this on the calculator, but I'm going to get it and take it the other side. If you take it the other side, what does it become? To become a positive value because it's now negative. I'll write it on top there. So I'll say plus half is the same as 0.5. I'll multiply by 58. And then I'll multiply by, this is supposed to be 3.6 squared. Remember it's velocity. So that has given me 1000, this is like a 10,000 and 21.16454, and that will be equal to half times 58, but 2 into 58 is a 29 v squared. Divide both sides by 29. So v squared is going to be 34.557. Square root both sides. So v has given me 18.58 meters per second. So when you're using the work energy theory, this is what you are going to find, 18.58. Is there anyone that has a question before we use the other method, conservation of energy? So for conservation of energy, what you do is you consider the energies at the beginning and then the energies at the end. They should add up, they should be the same. That is it about conservation of energy. It's very easy, guys. Okay. So for conservation of energy, at the beginning, what do we have? At the top here, this guy has got potential energy. So we're going to take it again like this, just like we did the other question. From where he is to the point where he is going to be, we are interested in knowing this height. So I'll say at the top he has got potential energy. What other energy does he have? Let me write it here. Potential energy. Remember, he already has velocity at that point, meaning that he also has kinetic energy. Okay. So these two energies, they are going to be equal to, as you go down, as you slide down, you are going to convert the energy to kinetic energy because you'll be moving at this point down. But remember, there is friction in this motion. So some of the energy that you had at the beginning will be used to overcome friction. So there will be work that will be done against friction. So at the beginning, you have got mgh. That will be equal to, oh sorry, not yet an equal sign. So we'll add the kinetic energy, half mv squared. But remember, this is v1, the one at the top. And this will be equal to kinetic energy at the bottom. That will be half mv squared. This is v2. Plus work done by friction, which is force times distance. Now for this side, I've not used the force negative. Why? Because it's already over the other side of the equation. If I had included this work done by friction on the reactant side, it would have been negative because it would be subtracting from the initial energy that we have. If we put it on the product, it's the energy lost. So just by virtue of being on the product means that you are negative because you're subtracting from the other side. So the mass, we know this is a 58. G is 9.8. The height, remember we said that how do you find height is d sin theta. The distance we are covering is 57. Sin the angle is 25. And then plus half. The mass again is a 58. The velocity at the beginning is a 3.6. And that will be equal to half. The mass again is a 58. The velocity at the end we don't know, we square that. Then plus F. This friction, remember we are told that there is a friction of 71. And then multiply by the distance, 57. So we'll punch 58 by 9.8 by 57 sin 25. So that has given me 13,692.32. I'm going to add 1 over 2, which is 0.5, times 58 times 3.6 squared. Then I'm going to get this term and take it to the other side to become minus. So minus 71 times 57. So it has given me 10,021.164. That will be equal to 2 into 58 is 29 v squared. To remain with v, divide both sides by 29 and then square root, because it was v squared. So that has given me 18.58 meters per second. So that is how you work out. For both formulas will give you the same answer. A boy and a sled weighing 300 newtons slide down an ice covered, and this is frictionless, hill AB from the top to the bottom. At the bottom of the hill, there is an ice-free patch BC. The horizontal surface brings the sled to a stop within a distance of 27 meters. So by the time you are reaching here, you stop moving. What is the coefficient of friction between the sled contact runner and the horizontal patch? So the horizontal patch actually has friction, but the mountain itself doesn't have friction. So here there is a friction. So what are we going to do for this one? For method 1, let's use again conservation of energy. So for conservation of energy, look at the energy at the top and the energy at the bottom. So we are going to first take A and B alone. So at the top A, you only have potential energy there. Because the hill is frictionless, by the time you are reaching B, all the potential energy is converted to kinetic energy. So therefore, potential energy is going to be equal to kinetic energy. And potential energy is given by mgh, and that will be equal to half mv squared. Masses are cancelling out. Get these two in the denominator, multiply with the gh. So find that v squared is equal to 2gh. Square root both sides, you find that v is the square root of 2gh. So that will be square root of 2 times 9.8 times the height. You can see the height there is a 10. And 2 times 5.8 times 10 to find the height. So 2 by, this is 9.8. Let's grab it. And then times 10. Then square root. So that's a 14. That's the energy at the bottom here. It's only kinetic energy. Remember, we're using conservation of energies. So this kinetic energy, as the object now starts to move from B to C, is going to be converted, because by the time you are reaching the point C, you would have stopped moving. So the final velocity at that point is going to be 0, right? So when you do this, you using energies again won't really add up, because what energy do you have here? If the object is not moving, you don't have potential energy. At the same time, the object is not on an elevated surface, you don't have kinetic energy because the object is not moving. And you don't have potential energy because the object is not on an elevated position. So in this case now, we'll just bring in some few laws of motion. So we can find the deceleration from the point B to the point C, since it's coming to rest. You can say v squared is equal to u squared plus 2as. Final velocity at C is 0. The initial velocity at B we found 14. And then plus 2a, the distance is 27. Okay. We'll take this 2a the other side. and that is going to be 2 by 27, and then by a it will actually become negative, and that will be equal to 14 squared. So to remain with a, we'll divide both sides by negative 2 times 27. So therefore the acceleration is going to give us, let me just punch that again, 14 squared divided by negative 2 by 27. That is a negative 3.6296 meters per second squared. Having found the acceleration or the deceleration now using Newton's second law, we know net force. When this object was at this point, there was no force pulling it forward. It was just moving because of that ability to slide. But because this surface is friction, there is friction there, so there's a force going in the opposite direction. So say net force is equal to what? Do we have any forward force? No, it's zero. How about a backward force from B to C? There is friction. But remember Newton's second law of motion, it tells us that a net force is mass times acceleration. So that will be equal to negative Fk, which is negative mu k times normal force. On a level surface like this one, the normal force is given by mass times gravity. So the mass cancels. The acceleration we just found, negative 3.6296. That should be equal to negative mu k times g, which is 9.8. So to remain with mu k, divide both sides by 9.8, and the negative will cancel. So that will give us 0.37. So this is how you do it when you are using conservation of energy. How about for the same question if you wanted to use work power and energy method? Are we okay with what we've done? Is there anyone that's behind? Okay, please feel free if there's anything that you're not clear with. Okay, so let's use the uh, uh, work energy theorem. You know, according to the work energy theorem, the work is equal to change in kinetic energy. Now, the work that is done is, we are saying, is going to be equal to the change in kinetic energy. But specifically, where are we interested? We are interested in this region if we want to use this method. The work that is done by the object to move from the point B to the point C should be equal to the change in kinetic energy from the point B to the point C. Meaning that I need first to find the velocity at the point B. To find the energy or the velocity at the point B, we'll still use energies which are conserved. The energy on top is equal to the energy at the bottom. So I can simply borrow, because we had already calculated velocity from the previous question to be from the previous method to be 14 meters per second. And then now from the point B to the point C, that's when we can use conservation of energy. Not really conservation energy, but work energy theory. If I wanted, I could have used work energy theory on top here to find the velocity, and then use work energy theory here to find the velocity. I would have done it. We know the object on top just as a, so the work that is going to be done on top, the object, there's a force that will be pushing it downwards. And in that case, we call it Fg, but we don't have an angle here, remember. Okay, because it was supposed to be Work was supposed to be equal to what? The force due to gravity times distance. And you know the force due to gravity is given by what? Mg sine theta, and then times distance. And that should be equal to a change in kinetic energy. At the beginning, we don't have a kinetic energy because we are on top and we are not moving. At the bottom, we have got kinetic energy. So meaning that the final minus initial, it will only be final. Okay, kinetic energy will just be half mv squared because the initial is 0 at the top. That will be equal to half mv squared. But remember what we said earlier, we said that height is given by what? D sine theta. So where there is d sine theta here, we are going to put the height. Can you see that the masses are cancelling out? So this will be gh is equal to half v squared. Cross multiply. If you make v substitute the formula, it will give you square root of 2gh. And it is the same thing that we did 2 by 9.8. The height is 10. That gave us a 14. So we have found 14 from the work energy theory. Again, now from the point B to the point C, work is change in kinetic energy. But from the point B to the point C, the only work that is present here is the work done against gravity. Okay? Work done against gravity. And how do you find that work? Because what you do is that you look at the object at this point. What are the forces acting on the object at this point? The only force that you have is a backward force, which is friction. The other forces are up and down, and those are going to give you a work of 0. So therefore, work is going to be friction times displacement. And that will be equal to change in kinetic energy at the bottom here. It will be final minus initial. But the thing is that the final energy here is 0 because it came to rest. But the initial is now the one that will be there. Why have I put a negative? Because the final is 0. And so we are going to put, remember, so for friction, we always put a negative here when you're finding the work done by friction. Why? Work done by friction is always a negative work. So where there is friction, we'll put coefficient of friction times normal force. On the level ground, normal force is mg times distance, and that will be equal to negative half mv squared. This mass will cancel with this mass. So substitute now negative mu k. G is 9.8. The distance covered is 27, and that will be equal to negative half. The velocity at this point we've already calculated, that's a 14 squared. So 9.8 by 27, that's 264.6 mu k. And that will be 14 squared divided by 2, that's a 98. So mu k, remember this is negative. Mu k is going to be 98 divided by 246.6. Oh, sorry, 264.6, and that's a 0.37. So that is how you work out that one. Okay. And then the last question. A fireworks displays a rocket in short straight. Okay, at a fireworks display, a rocket is shot straight up into the sky with a speed of 30 meters per second. So I've got something that is being shot straight up. Okay, straight up. And it has been shot with a speed of 30 meters per second. How high is it? when its speed is 10 meters per second. So when you reach 10 meters per second, use the energy method, assuming no energy is lost. So when you are using the energy method, again, what is the energy that you are going to have at this point? So using that method, you need to know the height that we would have covered for us to move from this point to that point. What is the height there? To find that height, we'll say 2gh is equal to v squared minus u squared. So 2, 9.8 is supposed to be negative because we're going up, times height. The final velocity is a 10 squared. The initial is a 30 squared. So it will be negative 19.6 h is equal to 10 squared, that is 100, minus a 30 squared, so that gives us a negative 800. Negative 800 divided by 19.6, which is also negative, to give us a 40.816. So using energy methods, at the bottom here, because it's the bottom, the only energy we have is kinetic energy. And as the mass goes upwards, at this point, since it's the maximum point we are taking, at the maximum point we don't have, we of course we have got some kinetic energy there that we can see, so we still have kinetic energy, but we also have potential energy because we are at a certain elevation. Kinetic energy is half mv squared, this is v1, and this will be half mv squared, and this is v2 plus mgh. The masses cancel out, so this will be half the first velocity, this is at the bottom, that's a 30, square that will be equal to half velocity at the top is a 10, square that plus gh 9.8 times the height. So what is the question asking us? How high? So that is times height. Okay, so I actually already calculated. Anyway, already determined the height. Okay, I used forces to find the height. So we can also use conservation of energy. So this will be half 30 squared is a 900 divided by 2. This is a 450. That will be equal to 10 squared is 100 divided by 2. That's a 50. Then plus 9.8h. So 450, if this 50 goes the other side, it will be negative. So we'll have 400. That will be equal to 9.8h. So h is 400 divided by 9.8. That gives me a 40.81. So you can use forces, you can use free fall, you find the same answer. You use conservation of energy, you find the same answer. How about if we use the work energy theory? We'll say work is change in kinetic energy. Work. What is doing work here? Because we are going upwards, the work is actually work done by gravity, which is mgh. We are going upwards. Work done by gravity is negative, isn't it? And then change in kinetic energy. The final kinetic energy will be half mv2 squared minus half mv1 squared. The masses again will cancel out. So this will be negative. G is 9.8. The height is what we don't know. That will be equal to half. The velocity at the top is a 10 minus half. The velocity at the bottom is a 30. That's a square. So here we'll neglect that g is negative because we already attached this negative in front of the formula. So this is negative 9.8h being equal to 100 squared 10 squared is 100 divided by 2, that's a 50. 30 squared is 900 divided by 2, that's 450. So I've got 9.8. H is equal to 50 minus 450, that's negative 400. H will still give you 40.81. It doesn't matter whether you use forces, conservation of energy, or you use work power energy theorem, the answer comes out the same.